So, hello everyone. So, today we are going to start the week 12. So, we will continue the some remaining part of week 11, that is on product recovery as a part of downstream processing, and in addition we will be discussing about bioprocess economics in this module. So, in the last module what we discussed about the importance of downstream processing, particularly that how much it accounts for the total cost of product. It may vary up to 50 to 80%. So, it is very important to go for the efficient and minimum number of steps in downstream processing, because as we increase the number of steps, so of course recovery and increases, but at the same time yield decreases and cost also goes up. So, we discuss various techniques used in the product recovery. So, it start with first separating the cells. Now, there can be products in three different categories. One, your cell itself is a product, second is intracellular product, and third is extracellular product. In either case, the first step will remain same. You have to go for solid liquid separation, and in that case we discuss about the filtration, sedimentation and centrifugation. Now, the second steps comes this cell separation and disruption. If it is intracellular product, then you have to go for cell disruption. So, there we discuss various mechanical as well as non-mechanical methods. So, in the mechanical we apply the shear and forces, in non-mechanical we apply the different chemicals and detergents, even in enzymes to break the cell wall, so that the internal material can release. Then after the separation and disruption of the cells, we have to separate the cell debris, then we have to go for the first isolation step. So, that is primarily the concentration step. So, there we discuss the extraction, particularly we discuss the solvent extraction, how it works, what is the role of choosing a solvent, particularly based on the distribution or partitioning coefficient. And next topic we also discuss about the chromatography, that how the selection of different stationary phase decides the different mechanism of chromatographic separation, and accordingly the different techniques are named like ion exchange chromatography, affinity chromatography and so on. So, in today, in continuation of the downstream processing, we will be discussing on adsorption. So, the first thing we will be discussing what is adsorption and how it is important in downstream processing. Then what are different type of adsorbent materials. Then briefly we will be comparing this difference between absorption and adsorption. Then we will go ahead with adsorption process, what is the physical and chemical adsorption. Then there are few adsorption isotherms that we will be discussing. The adsorption, as the name suggests, it is a physical process as a surface phenomena. So, in this case what happens, the molecules from a fluid accumulate on a solid material, and it may form a thin film, it may also form multilayer. Now, what is adsorbent? The solid material is called the adsorbent, where molecules or adsorbate will be attached, and adsorbate means that substance or compound that gets adsorbed on the solid surface, that is the adsorbate. And in case of downstream processing, adsorbate is your molecule of interest. In binding sites or ligands, so it says the location on the surface of adsorbent where the solute molecules bind. and because of this adsorbate interactions, depending on their physical and chemical properties, there may be different kind of intermolecular interactions that may include simple van der Waals interaction. If they are charged, oppositely charged, it can be electrostatic interaction. There can be some reactive interaction also, formation of hydrogen bond, formation of some other interatomic bonds, or there may be the other binding like hydrogen, hydrophobic interaction, hydrogen bonds. So, once your adsorbate is reaching to the surface for the adsorption can be distinguished, it can be exchange process, it can be physical adsorption, chemical adsorption, or it may be the random or unspecific adsorption. That we will be discussing again in the next slide. So, it says why then adsorption is a surface phenomena, because only the surface of your adsorbate or solid material is involved in attracting and holding the molecules from another phase. So, typically the bulk interior of adsorbent materials remains unchanged. So, this is how it is called surface phenomena, and there are different factors as the surface is involved, its surface energy, its active site, surface area, and surface energy is directly related with this surface hydrophobicity. Surface and surface area is related with surface roughness. Now, in bioprocessing, particularly the importance of adsorption. So, first is the product recovery in the downstream processing to isolate and concentrate a valuable product from the fermentation broth. So, for example, if you want to isolate insulin, recombinant insulin, typically the first step is the adsorption column. Then you can have the ion exchange adsorption, particularly for the recovery of amino acids, antibiotics, protein and vitamins. So, as I told insulin is a protein. So, for such cases we prefer this ion exchange adsorption, because in this case by simple changing the pH value, it turns the different kind of adsorption or interactions. In addition, adsorption is also frequently used in the wastewater treatment, because we can have a good adsorbent with high surface area, and once it is having a high surface area, it is going to have more and more adsorption capacity. So, removal of various contaminants like heavy metals, dye and other toxins. In biological process, the binding of signal molecule on the specific receptor site in the cell signaling pathway. In addition, nowadays in the biosensors, the first step is the interaction of your analytes or molecule with the biological agents, and biological agents are immobilized on a solid surface typically. So, in the biosensors also there are lot of importance on the surface adsorption. Now, type of adsorption, it can be the exchange, it is exchanging something is previously there on the surface that is being exchanged by the new material coming in. It can be physical adsorption through the physical forces like van der Waals interaction. It can be chemical if there is a chemical bonding taking place, or there is a random adsorption, which there can be multiple sites where adsorption is taking place and they are not following any particular sequence or particular trend. So, ideal adsorbent material, it should have this high surface area per unit volume, and typically the solid with fine internal pores that offers large internal surface. So, one is outer surface area, and if it is a porous material and if the molecule need to percolate inside, then it should have large internal surface as well. So, for this region, if you want to increase the surface area, we go towards the nanomaterials. Towards the nanotechnology. So, in the nanotechnology, you can increase very high surface area per unit volume. Now, adsorbent based on their nature, you can have mostly the inorganic like silica gel, metal oxides, zeolite, clay, metal hydroxide, activated carbon, molecular carbon, and carbon nanotube, molecular carbon sheaths. In addition, there are bio based or this bioresources we say like cellulose. Nowadays, we are going with nanocellulose, jute fiber, wood fiber, sugar beet pulp or sawdust is commonly used in the routine practice. In addition, now the synthetic adsorbents are also there, particularly various polymers which are being used in a ion exchange resin as a membrane surface for the adsorption or molecular imprinted polymers. So, it can be based on the nature, it can be inorganic, it can be bio based or it can be some polymeric materials. Further, you just see type of adsorbent particularly in the bioprocessing. So, activated carbon is mostly used. If you remember in household setup for the water purification, we use this activated carbon. So, basically it is used for the decolorization and removing organic impurities due to its high surface and porosity. Ion exchange resins, they selectively bind proteins via this charge interaction and adding to effective protein purification. Silica gel is another popular adsorbent. It is effective in separating the small molecule and frequently used in chromatographic applications. Affinity resins provide very high specificity because they have certain ligand groups present on the surface. By binding particular biomolecules, this is ideal for monoclonal antibody or other specific protein purification. Now, when we go for the adsorption operation, there are multiple steps involved. The first is your adsorbate should come into contact of adsorbent surface, their adsorption takes place. The first step is it should come into contact and the contact should be for a given duration. So, particularly you can say we typically say it is optimum condition. It may also include temperature, it may also include the pH. So, that the loading of solute to the adsorptive resins or the adsorbent takes place. Now, next step is you have to remove the residual or unadsorbed material. So, this is called the washing step. Now, third step is the elution or the desorption. Now, we have to remove this concentrated adsorbate material with suitable solvent. Now, once you have removed, again you have to wash to remove the any residual elutant, and then next step is as you have to reuse the adsorbent for multiple cycles, you have to go for regeneration. Then you regenerate, you remove the impurities and regain the adsorptive capacity of your adsorbent. Now, quickly we will see the difference between adsorption and absorption. So, both are having the interface. In this case, typically in the case of adsorption, the interface is solid, and when we say it is absorption, the interface is typically liquid. So, if you are dealing with solid liquid interface, where the molecules from liquid is getting adsorbed at the solid, it is called adsorption. But when you are let us say having the gas liquid interface, the molecule from gas is getting adsorbed in the liquid, so that is called the absorption. So, here I have put a quick comparison between adsorption and absorption. So, adsorption is a bulk phenomena mostly in the liquid phase, and this is a surface phenomena adsorption. Phase involved, it occurs through the volume of the adsorbing material, and adsorption occurs at the interface. Type of interaction, in case of absorption, this is the weak physical forces, it may be hydrogen bonding. In case of adsorption, it can be van der Waals forces, then it will be physical adsorption, and if there is a chemical bonding, then it is called chemical adsorption. Reversibility, as it is hydrogen bond, so it is irreversible if there is no chemical reaction involved, and adsorption is also reversible because typically you are able to elute and regenerate your adsorbent. Heat involved, it may be exothermic or endothermic, and adsorption is mostly exothermic. Influence of temperature, so in case of absorption, of course solubility changes, but effect may not be so significant, and in case of adsorption, it directly affected by the increase in the temperature. If you increase the temperature, typically the rate of adsorption increases. Reaction speed, this is a slower because it requires the diffusion into bulk, and this is typically faster because this is taking place only at the surface. Saturations, this occurs when adsorbent cannot dissolve or react, and this occurs when there is no more active surface is available for the more adsorption to take place. Common methods, so it is only monolayer, it follows Langmuir isotherm, and no, it will be in the case of absorption, it follows the Henry law of saturation, and in case of adsorption, it follows typically the Langmuir isotherm, the monolayer coverage. One quick example is absorption of oxygen in the blood or absorption of oxygen in the fermentation media. And one quick example for adsorption is activated charcoal in water purification adsorbs impurities. Another example is you can see the adsorption of proteins using ion exchange reagents. Now, we can classify the adsorption based on the nature of forces, number of layer and reversibility. So, based on the nature of force, one can say physical adsorption or chemical adsorption. Number of layers, monolayer and multilayer, reversibility, reversible or irreversible. So, typically when there is a not very strong binding with the surface, we can achieve the reversibility, but in the case of very strong binding, it is difficult to achieve the reversibility. So, physical adsorption, in this case adsorbate adheres to the surface of the adsorbent through physical interactions like weak intermolecular forces, let us say van der Waals forces. So, there is no chemical bond formation in this case, and typically this BT isotherm is able to explain this physical adsorption properly, and this always lead to the multilayer adsorption depending on the nature of your surface and the availability of your adsorbate molecule. In the case of chemical adsorption, there is a formation of a chemical bond with the adsorbent, and it involves this chemical interaction. It may be the covalent, it may be the ionic interactions, and for this there are different isotherms which explain this process like Langmuir isotherm, and as this is very specific to the chemical bond formation, so mostly it can be monolayer unless and until there is a secondary or the other chemical reaction is taking place on the pre-adsorbed layer, then only it can be multilayer, because some chemical reaction is taking place, and once all the active sites are covered, typically that reaction should cease. So, van der Waals interaction, it occurs between adjacent uncharged and non-bonded atoms. So, this is non-covalent, non-specific and short range force, and it arises from induction of dipoles due to fluctuating charge density within atoms. However, this van der Waals interaction, it does not follow the Coulomb's law of electrostatic interaction, and it acts as initial weak interaction in the case of chemoabsorption as well, and bond strength for this force is about less than 50 kilojoule per mole. In the case of ionic bond, particularly it is electrostatic interaction. So, it is taking place due to opposite charge ion, and it follows the Coulomb law of electrostatic interaction. So, it enables a strong and stable interaction between adsorbent and adsorbate. It is highly specific, and bond strength is, of course, it should increase. So, it has increased in the range of 600 to 1000 kilojoule per mole. Further, if you see this covalent bond, so this in this case the bond strength will further increase because of exchange of electron pairs during the formation of covalent bond. Now, once adsorption is taking place, then with time it should reach to the equilibrium. So, further the understanding the equilibrium relation between bound and the free solutes. So, we say isotherm means the equilibrium between free solute molecule in the liquid phase and bound molecule over the surface of adsorbate. Once the equilibrium is reached, means there will be no more adsorption. So, adsorbent and adsorbate are at equilibrium. So, this defined distribution of solute between solid and the fluid phase, and after the equilibrium no further net adsorption occurs, and adsorption equilibrium data they can be fitted to various isotherms to predict some model parameters. So, adsorbate A at given temperature, then isotherms give the concentration of A in the adsorbed phase versus concentration of in the unadsorbed phase or the bulk phase. So, particularly you just see this says the let us say Q and this is the C. So, plot between Q and C it typically gives the equilibrium relation, and we consider as the isotherm. So, simplest one is you just say Cb solute bond per unit area of adsorbent is directly proportional to the Cu, it says concentration of unbound solute. So, whatever concentration was there, this adsorption is directly proportional, and proportionality constant we say Cb is equal to K into Cu. So, this is very simple linear isotherm. So, it has made certain assumptions like low surface coverage, solute concentration is very low, no competition between adsorbed molecules, no multilayer adsorption, and equilibrium happens between adsorbed and bulk phase. Next one commonly implied is the Friendly's isotherm. So, this is an empirical relation, it does not have any theoretical basis for this model. So, it says CAS equilibrium concentration of loading A on adsorbent, concentration of surface is proportional to the Ca concentration in the bulk at equilibrium to the power 1 upon n, and proportionality constant is the Kf, or it is a Friendly's constant, and typically depending on the value of n, if n is greater than 1 the adsorption is favorable and it may lead to multilayer adsorption, and if n is less than 1 it means adsorption is not favorable and it will stop with a single layer adsorption. So, you just see Ca versus Cs, this is a typical curve of the Friendly's isotherm. So, it is widely used in solid liquid system and for the adsorption of antibiotics, steroids and hormones. This model have been found to fit better with the experimental isotherm data. So, it assumptions are its empirical model based on the experimental observations, and it says adsorbent surface is heterogeneous, there is no saturation point, and adsorption is not limited to monolayer, it can lead to multilayer adsorption, and heat of adsorption decreases with increasing the surface coverage. Next is the Langmuir model. So, it assumes the formation of monolayer on the surface, and it says the rate in this case is proportional to the theta, or you can say the available area. Available area or available active site for the adsorption. So, let us say if theta is the surface coverage, what will be the available area? It will be 1 minus theta will be then in that case available area for adsorption. So, Langmuir adsorption, it gives the concentration at the surface is proportional to the CAS maximum into Ka, that is the equilibrium constant. Ca is the equilibrium concentration of solute plus 1 upon Ka into Ca, and Ka is called the Langmuir constant. So, it fits to the many experimental data, particularly in bioprocess as well. So, it says typically there is no stacking of molecule, it lead to the formation of monolayers, and binding sites are all similar and homogeneous surface, no interaction between adsorbed molecules. So, it says it is not considering interaction among this adsorbed molecule itself, and ideal gas behavior, the adsorption and desorption process is reversible, then only you can reuse this adsorbent. So, mostly the adsorption process is performed in a batch mode. So, in that case the feed solution and adsorbent are brought into contact until they reach into equilibrium, and the spent solution or raffinate will be removed by the centrifugation, and the pellet it containing the adsorbent material bound with the solute. So, the next step is you have to wash it, and after the washing you have to dissolve your product. So, you just see general form of here the isotherm is, it says Cb is proportional to Cu, and proportionality constant, let us say this is a phi. Now, the solute, if I go for the solute mass balance, then initial solute concentration in the feed Cuo into the feed rate plus initial solute concentration in the adsorbent Cbo into A, that should be Cu concentration in the feed into S plus Cb into A is quality of adsorbent. So, it says you can simply do the adsorbent mass balance, how it is distributing among different phases. So, we go with the packed bed adsorption column, that is quite common, and it contains a cylindrical column, and this column will be packed with your adsorbent materials. It should have good surface area, it should have good porosity, it should be inert, and the material itself should not interact with and participate with any other kind of bonding. So, if you are using the column, it is easy to reuse those adsorbent after regeneration. So, what are the steps we discussed earlier? Adsorption, washing and then elution, then followed by that you have to go for again washing and regeneration. So, in typically this laboratory setup, we use the simple pump and to pass through this adsorption column, and at the end there is sample collector. So, there you can measure a decrease in the bulk concentration, and the decrease in the bulk concentration gives how much amount have been loaded or adsorbed on the surface. So, when you operate the column, so column starts getting saturated with time. So, there is one term called the breakthrough time. It says time duration until outlet concentration reaches to the same as the initial concentration. It means there is no more adsorption taking place in the column. I say column is saturated, and the breakthrough point comes when the ratio of CT to C naught is close to 0.05 or 1. So, there we stop the operation of column, and then you have to wash, regenerate, then only it can be reused. The feed solution passes through the packed bed beyond the breakthrough point. Then the concentration of adsorbate in the effluent rises slowly and finally reaches to the same feed concentration. So, you just see how it is taking place. The concentration, up to here the total adsorption is taking place, and slowly this unbound material is going out and it is reaching to plateau, and this value will be same to the initial concentration in the feed. And once it is there, then you have to stop here, then you have to go for this washing, and then you have to use another eluting solvent to go for its elution. Typically, you just see in the column how it looks like. So, it says there is a saturated zone and there is a adsorption zone. So, when the adsorption zone will move down, it means this zone is getting saturated. So, the size of, you just see the saturation zone will keep on increasing, and finally, the adsorption zone will leave out of the column. And once adsorption zone has left out of the column, you just see from here to here, up to here all the adsorbate was adsorbed on the surface, but now from here to here all of a sudden you just see the initial concentration is now the outlet concentration. It means the adsorption zone has come out of the column, and for such cases we see this dCAS upon dt equals KLA, mass transfer coefficient, divided by 1 minus epsilon porosity, and driving force will be Ca minus Ca star, difference in the concentration. Now, we will have a quick example here. So, it says cell free fermentation liquor contains 8 into 10 to the power minus 5 mole per liter of IgG, and it is proposed to recover at least 90% of this antibody by adsorption on synthetic nonpolar resin. And experimental equilibrium data is correlated with this. It says CAS moles of solute adsorbed per centimeter cube is given by 5.5 into 10 to the power minus 5 Ca to the power 0.35. Ca is the liquid phase solute concentration in mole per liter. Then here it says what is the minimum quantity of resin required to treat 2 meter cube of fermentation liquor in a single stage mixed tank. So, what we have to achieve? We have to achieve 90% antibiotic removal. So, what was the concentration? It was 8 into 10 to the power minus 5, and if you consider this 90% of this, then it will, what is the remaining is the 8 into 10 to the power minus 6 mole per liter. And now, this will be in the equilibrium with the surface. So, CAS is coming out to be 9.5 into 10 to the power minus 7 mole per centimeter cube. And once you got this CAS, then you can calculate the amount of adsorbed antibody. So, it says Ca 8 into 10 to the power minus 5, this into 90% plus the total volume is your adsorption is taking place from 2 meter cube. So, you are getting 0.144 mole of antibody has been adsorbed. Now, we have to calculate how much volume of resin is required. So, this is the amount of adsorbed antibody, and this is the adsorption capacity of your reagent. So, if you divide with this equilibrium adsorption capacity, so you will get the material required will be 1.6 into 10 to the power 5 centimeter cube or 0.16 meter cube. So, with this I will stop here. So, today we discussed the adsorption as a surface phenomena, then different type of adsorbent, and accordingly there will be different type of intermolecular interaction depending on the nature of both adsorbate as well as adsorbent. Then we discuss what are different steps in the adsorption process, starting with the loading or contacting, then washing, then elution, then again washing, then next is regeneration. In this way it can be recycled for the multiple sites, and once adsorption process is there, then there will be equilibrium data, and that gives you the flexibility to calculate this the equilibrium parameters based on the fitted models. Thank you so much.